The field of machine learning is taking monumental leaps. Each and every day there's a new machine learning model which is pushing what we thought was possible. We've seen the likes of Whisper, ChatGPT, DALL-E 2 and large language models. So I wanted to take this opportunity to help you build your very own game changer model. We're going to be teaching machine learning how to lip read. What's happening, guys? My name is Nicholas Renat, and in this tutorial we are going to be building our very own machine learning model that is able to read lips. Now all this code is going to be available as well as the data, so you're going to be able to build it up from scratch and get this up and running. Now Nick, why do we need to build a machine learning model that's able to read lips? Well, this is almost like an extension of the sign language model that we've built previously. It improves accessibility and gives society the additional power to be able to use machine learning for good. So how are we going to build it? Well, we are going to be using a range of technologies. We're going to be using OpenCV to be able to read in our videos, when we're going to be using Tensorflow to be able to build up our deep learning model. We're then going to bring it all together and test it out so that we're able to decode what a person might be saying. And again, this is going to be using a client conversation format, so you'll be able to get an understanding of what we are doing at each single point in time. Ready to do it? Let's go and have a chat to our client. Yo Nick, what's up Johnny? Not much. Oh no, this isn't one of your ML startup ideas again, is it? Actually, alright, what is it? I was hoping you could get me to use machine learning to do lip reading. Lip reading? Yep. What are you, the FBI? Why lip reading? Well, it kind of goes hand in hand with the stuff that you did around sign language, but flipped around. Okay, fair, interesting. I'll even give you 10% of the company. I'm gonna need you to code it all though. Alright, fine, let's do it. But not because of the 10%, because of you guys. Hopefully you enjoyed this tutorial. First thing we need to do is install and import our dependencies. Let's go get them, co-founder. Let's do this. We interrupt your regular programming to tell you the Courses from Nick is officially alive. If you'd like to get up and running in machine learning, deep learning, and data science, head on over to www.coursesfromnick to find the latest and greatest. I'm also going to be releasing a free Python for data science course in the upcoming weeks, so be sure to stay in the know. But if you're ready to hit the ground running, well, I highly recommend you check out the full stack machine learning course. This goes through 7 different projects, 20 hours of content, all the way through full stack production ready machine learning projects. Head on over to www.coursesfromnick/bundles/full-stack-ML and use the discount code YouTube50 to get 50% off. Back to our regular programming. Alrighty, so the first thing that we told our client that we would be doing was installing and importing some dependencies. So let's go on ahead and do that. Okay, so the first thing that we need to do is install a bunch of dependencies. So we've got our first line of code, which is pip install opencv-python, matplotlib, image.io, and gdown. Now we also need to add TensorFlow to this list if you don't have it installed already. Okay, so we're going to be using OpenCV to pre-process our data, and I'm going to show you where to get the data in a second. I've actually built a little script that's going to download it for you from my Google Drive. Matplotlib is going to be used to render the results, so we'll actually be able to see the outputs of our pre-processed videos. We're going to use image.io to create a quick little GIF, so you'll actually be able to see a couple of the frames stacked together. It looks pretty cool. Gdown is going to be used to actually download our data set, so it just works really seamlessly with Google Drive, and I think that's what I'm going to start doing for data sets going forward. And TensorFlow is going to allow us to build our deep neural network. So if we go on and run that cell, this should go on ahead and install all of our dependencies. That's looking pretty promising. If we want to go and take a look at the different versions of libraries that we're going to be using, we really should be moving this up. We can run pip list. And let's go and take a look. So we installed, I can't even remember what we installed now. We installed OpenCV-Python. Let's enable scrolling. So let's go and take a look at the version of that we are using. OpenCV-Python, we're using 4.6.0.66, pretty good. Matplotlib, the version of that we're using is 3.6.2. Image.io, where's that bad boy? Over here, so 2.23.0. For gdown, where is that gdown? Over here, we're using 4.6.0, and for TensorFlow, we are using 2.10.1. Also, this code is going to be available on GitHub. So if you jump on over to GitHub and go to Nick Knock Knack and go to repositories, this file is under LipNet. It's private right now, but I'm going to make it public. So if you actually go and take a look, I've included pre-trained model checkpoints, so you don't need to go and train this yourself. You can kick things off with a pre-trained model, and I've also included the Jupyter notebook. So just a quick git clone of that particular repository, and you're going to be able to get started with all the code that you see in here. Okay, so that is the packages that we need installed. So that is now open. All right, the next thing that we need to do is import a bunch of dependencies. So we are going to be importing OS. So the first line there is import OS. This is just going to make it a lot easier to navigate and traverse through different file systems. This is going to work a lot more seamlessly if you're working on a Windows machine or a Linux machine. There are a few nuances that I noticed that I had to do, particularly for the data splitting, but I'll explain that a little bit later. So first line is import OS. Our second line is import CV2. This is going to allow us to import OpenCV, which is going to be needed to pre-process and load up our videos. Then we've got TensorFlow. So import TensorFlow as TF. That's going to be our primary deep learning framework that we're going to use. We're going to use TensorFlow data pipelines as well. So if we actually go and take a look, TensorFlow data pipeline. Take a look. So TF data. Now, this can be a little bit tricky. So I always try to evaluate whether or not this is better doing in TensorFlow versus PyTorch. Who knows, maybe at some particular stage I'll actually go and transition, but I've got this working. So tf.data is a great data pipeline framework. It allows you to actually go and transform data. Can be a little bit tricky at times. So sometimes you do need to do some stuff that is a little bit slightly nuanced, which is going to be unique regardless of which deep learning framework you're using. But we're going to be using a proper TensorFlow data pipeline, which is probably a lot more closely aligned to proper machine learning operations. So we are going to be building up our data pipeline using the tf.data API. Okay, the next thing that we're importing is NumPy. So import NumPy as NP. It's always just good to have NumPy along for the ride if you need to go and pre-process any arrays. I've then imported typing. This is something that I've sort of personally taken on as a little bit of a challenge or stretch goal this year to effectively start using type annotations a little bit better. I'm not great at it, but I am improving, hence why we're going to be using the list type annotation. We've then imported matplotlib, so we've gone and written from matplotlib import pyplot as PLT, so this is going to allow us to render the pre-process or post-process output of our data loading function. And then I've also brought in image.io. There's like a one-liner which allows you to convert a NumPy array to a GIF, which looks really cool, and you're able to see what you've actually gone and pre-processed, which is particularly useful when you're dealing with videos. Okay, those are our imports now prepared. So import OS, import CV2, import TensorFlow as TF, import NumPy as MP. We're going to import typing. We're going to import matplotlib and image.io. Those are our dependencies and now imported. The next thing that we need to do is just prevent exponential memory growth. So if you're running this on a GPU, which I highly recommend you do, whether that be Colab or some other sort of cloud service, or if you've got a GPU on your machine, which is CUDA enabled, highly recommend you run this line because it's going to prevent your machine from sucking up all the memory and getting out of memory errors. So the full line, and you've probably seen me use this a bunch in other deep learning videos as well. So first up, we're going to get all of our physical devices. So physical underscore devices is equal to tf.config.list underscore physical underscore devices. So if I actually grab this line here, and we should need to actually run our import. So let's let that run.
5 minutes later.
Now import, if I actually go and run this, we should be able to see which physical devices we have on our machine. So you can see I've got my one GPU showing up there. Basically, what we're then going to say is we are going to prevent any exponential memory growth. So tf.config.experimental.set memory growth, and we are going to assign that to our one GPU that we've got here, and we're going to set it to true. But if we do have a GPU, then we're going to be able to successfully set that. If we don't, then we're just going to pass. So we can then go and run this. And you need to do this pretty much straight away before you go and do any modeling or anything. Otherwise, it's not going to take. Okay, that is our set of dependencies now imported and installed and imported. So just to recap, so we've gone and import or installed OpenCV, matplotlib, image.io, gdown, and TensorFlow. And then we've gone and imported all of our dependencies. And we've also gone and set our memory growth limit to true for TensorFlow. This is particularly applicable if you are training on a GPU. Okay, those are our dependencies now installed and imported. Back to our client. All right, so we're gonna be working with the grid dataset for this. Nice. Is this something that we'd eventually be able to use with a custom dataset, say ourselves? Sure, I've actually got this plan. We just need to capture frames of a person speaking, then use a speech-to-text model to transcribe what they're saying. That dataset could then be subbed into the model training pipeline. Let me know if you want that tutorial. Got it. So the grid dataset for now? Yep, we need to build 2 data loading functions, one to load the videos and one to load the aligned transcriptions. Got it, let's roll. Alrighty, so now that we've gone and installed and imported our dependencies, the next thing that we want to go on ahead and do is build our data loading function. So there's 2 key data loading functions that we're going to need to build here. The first is to load up our videos, and then the second is to actually pre-process our annotations. And our annotations in this case are sentences which our particular person in the videos has actually gone and talked about. Now, the data set that we're going to be using is an extract of the original grid data set. So this data set was built to be able to go and build lip reading models. Now, I've gone and made your life a little bit easier by just loading this data into my Google Drive. So you're just going to be able to download the specific sections or parts that I use to actually go ahead and build this, and that you're going to be able to go on ahead and build this. So first things first, what we need to do is import gdown. So that full line is import gdown, and gdown is a library that just makes it super straightforward to go on ahead and grab data out of Google Drive. Once you got that, the next thing that we're going to go on ahead and do is download the data itself. We are going to output it inside of a file called data.zip, and then we'll extract it all into its own separate folder. So the full line is URL equals, and then I've got this specific URL here, so you can actually grab that, paste it into your browser, and you'll be able to download the data set. We're just going to use Python to do it because it makes your life a ton easier. We're going to output the file to a file called data.zip. We're going to use gdown.download. To that, we pass through the URL, which is this over here. We also pass through the output file name, and we've set quiet equal to false. We can then extract it as well, because we're going to be downloading it as a zip file. We don't need it as a zip file. We need it unpacked. So we can use gdown.extract all and pass through data.zip to be able to go and extract that. So if I actually go and run this, you'll see it should start downloading our data. And there you go, we're now downloading data. So it's around about 423 megs. This is only one speaker. The original grid data set, I think, has something like 34 different speakers. So if you wanted to extend this way further out, specifically using the grids data set, you definitely could. But I'm going to take this a different direction later on, and we're actually going to grab data of ourselves and be able to train it on that. So let's let that download, and then we'll be able to kick things off. Psst, come here. Want to know a secret? Are you looking for your next dream job in data science, machine learning, deep learning, or just data in general? Well, you need to join Jobs from Nick. Each and every week, I'll send you a curated list of the best jobs in data. These are jobs with great perks, great people, and great roles. Plus, you'll get access to exclusive content like AMAs, interviews, and resume reviews. So why not join? Plus, it's completely free. Link is in the description below. What are you waiting for? All right, back to the video.
A few moments later.
Alrighty, so that is our data now downloaded. You can see that we've gone and successfully downloaded it there. Now, if we actually go and open this up, you'll actually see that we have got our data.zip file now downloaded, and we've also got this new folder called data, which is what the extract all function would have done. App is something that I got planned for in the future. If you want to see this as part of a Code That episode inside of a full stack app, let me know in the comments. But we are most interested in this over here. So this data folder. So if we open this up, and this is what this section or code cell is going to create. We're going to have a file called alignments, and inside of that, a file called S1 or a folder called S1. And this represents all of our annotations. They're in this .align file format, which is interesting to say the least. If you open them up, this is what an annotation looks like. Now, these specific videos are really around moving certain things to certain places. So sil means silence, and then we've got these different commands. So bin blue at F2 now. If we go and take a look at another one, let's scroll on down. There's this one, lay white by F5 again. So you can see that it's not necessarily things that you'd encounter out there in the real world, but we're definitely going to be able to train a model to be able to decode this from purely a video, no audio. So still means silence. So we were actually going to get rid of those when it comes to pre-processing annotations, but we want to really extract this. So we want lay white by F5 again. And then in this particular case, we'd want bin blue at F2 now. Now, if we actually go and take a look at the videos, we've actually got videos in here as well. So if I jump into our S1 folder, so if I go into my root folder, so data, and then S1, and then you can see I've got MP4s here. So that's not going to play within, inside a Jupyter Notebook. So let's actually just open it up. So if I go into the folder that I'm currently working in, and we go into data and we go into S1, you can see I've got all of these MPEG files, right? So these are all of our videos. If I go and play one.
Bin Blue F4, please.
Let me chuck my headphones on.
Bin Blue F4, please.
Bin Blue at F4, please. So you can see that we've got different videos of a particular person saying something. Now, eventually,
Blue by C7 again.
Place B blue by B7 again. So you've actually got matching annotations, right? So if we go and open up a specific annotation, go to alignments, S1, and go and open up this one. So BBAF2N. This should effectively represent the annotation for the matching video. So bin blue at F2 now. So if we go and find that particular video, which should be the first one. So BBAF, let me zoom in. Boom, boom, boom. BBAF2N. So we should be able to go and play this.
Bin Blue F2 now.
Right? So it just said bin blue at F2 now. Bin blue at F2 now. So this is the data that we're going to begin working with. Now, that is our data now downloaded. The next thing that we want to go on ahead and do is actually get this into a data loading function. So I've gone and written this function called load video. This is going to take a data path and then it's going to output a list of floats, which is going to represent our video. So what we do is we first create a CV2 instance, a video capture instance, which takes in our path. And then we're going to loop through each one of these frames and store it inside of an array called frames. What we then do is we reduce them, or we calculate the mean, we calculate the standard deviation, and then we standardize or scale our particular image features. So we subtract the mean and we divide it by a standard deviation. I'm also doing something here, which is effectively isolating the mouth region. Now I'm doing this using a static slicing function. So I'm basically saying, go from position 190 to 236 and position 80 to 220 to isolate the mouth. There is a slightly more advanced way to do this using a specific face detector to extract the lips, which is what the original LipNet paper actually does. So if I show you the LipNet paper. So LipNet actually uses, I think it uses dlib to be able to go and extract the mouth. So if I go dlib, search from within here. dlib. Yeah, so they use dlib to be able to go and isolate the mouth. Now, I've just gone and done it statically for the sake of keeping this relatively straightforward, but that is effectively what we're doing there. So we're looping through every single video. We're storing the frame inside of our own set of arrays. We're converting it from RGB to grayscale as well. That means that we're going to have less data to pre-process, and then we're isolating the mouth using this static slicing function. We're then standardizing it, so we're calculating the mean, calculating the standard deviation. That's just good practice to scale your data. And then we're casting it to a float, 32, and dividing it by the standard deviation. So if we go and run that, that is our load video function now done. Now we're going to go on ahead and define our vocab. Now our vocab is really just going to be every single character which we might expect to encounter within our annotation. So bin blue at F2 now. We've also got a couple of numbers in there as well, just in case we need them. So if I go and run that, and we can actually go and take a look at our vocab. So you can see it's just a list which contains each and every potential integer there. Now the cool thing about this is that we can actually go and use the Keras string lookup function to be able to go and look up or convert our characters to numbers and our numbers to characters. So over here, you can see I've got char to num, and this is originally from the Keras CTC, I think it's ASR tutorial. So it actually uses this specific loss function to do automatic speech recognition. So I've actually thought that this was a really neat way to do it, and it keeps everything nice and clean. So we've got two functions here, char to num and num to char. The first one takes a character and converts it to a number, and the second takes a number and converts it to a character. So it just makes your life a ton easier when it comes to actually converting text to string and string to text. So if I go and type in char to num, I think we can go and pass through, let's say, A, B, C. And you can see it's converting it to 1, 2, 3. Now, if I went and typed in N, I, C, K, should be a comma. you can see it's converting each one of these characters to an integer over here. So this is effectively not necessarily one hot encoding our data set, but it is tokenizing it and returning a specific token value or an index effectively. Now we're going to be able to pass through this data to our loss function to be able to calculate our overall loss, because our model is going to be returning a one hot encoded version of this. Now, likewise, we can actually go and decode this. So if I go and use num to char, and if I pass through this array, which is 14, 9, 3, and 11, we should get the reverse, which gives back Nick. Boom, and you can see that there. So it's a byte encoded value, but you can see I've got N-I-C-K. So these are going to be our lookup functions that allow us to convert and reconvert our text to encodings. Okay, that is our vocabulary now defined. So the full line there is char_to_num is equal to tf.keras.layers.string lookup. We pass through our vocabulary, and then we're setting out of vocabulary token. So if it encounters a character that it hasn't seen before, it's just going to be a blank value. Then we're doing the opposite. We're creating a num to char function, which is equal to tf.keras.layers.string lookup. We are then going and passing through the reverse, so we can actually go and get our vocabulary out of this. So if I type in char to num .get vocabulary, boom, you can see it's just returning back all of our unique characters. Beautiful. Again, we're setting out of vocabulary token, and we're using invert equals to true to say that we want to convert numbers to characters, not the other way around. Okay, and then we're printing out our vocabulary and the size. All right, and then we're going to use a function to actually load up our alignments. So our alignments being these, we are going to take in a specific path, which eventually is going to map through to these paths. So alignments /S1. We're going to open up that path, and then we're going to split out each one of these lines. If the line contains the value silence, we are going to ignore it because we don't necessarily need it. We're then going to append these into an array called tokens, and we're going to convert them from characters to numbers. So we're going to go and split that data out and convert it into a set of characters. Now, there's one last thing that we need to do before we can go on ahead and test this out. We need to go and load the alignments and the videos simultaneously. So we're going to extract both of those paths, and we're going to return the pre-processed videos and the pre-processed alignments together. So we need a load data function. So this is going to take in the path to our video. We are then going to split it out and convert it so that we have a video path and an alignment path. What we're then going to do is we're going to use both of our functions. So we're going to use our load video function and our load alignments function over here, and we're going to return the frames and the alignments out of each one of those functions. So if I go and run that, what we can then do is get a test data path. So if we just go and grab this particular video, which is our first one, so BBA16N, and then what we can go on ahead and do is pass that to our load data function, which is what we had here. I'm going to wrap that specific path inside of our tf.convert to tensor function. And this is just going to convert a raw string to a TensorFlow tensor. So tf.convert to tensor. If I pass through test path, you can see we're going to get a tensor back. Now to grab the tensor value, we can type in .numpy, and that's going to grab that. And then I believe we can type in decode, and it should be UTF-8, and then we're going to be able to grab that specific path. Inside of our load data function, what we're doing is we're actually splitting. Now, if you're running this on Windows, you're perfectly fine to run this as is. If you're going to run this on a Linux or Mac machine, comment this line out and uncomment this. So this is going to be, I believe, to be able to run it on a Linux machine. I had to play around with it when I was running it on Colab versus running it on my Windows machine. So that's the only change that you do need to go and make if you're going to run it on a different type of machine. So I'm going to comment that out and leave the Windows bit open. So what we'll effectively be doing is we'll be grabbing this string and then we'll be splitting it. So if I type in .split, I'm going to split on the double backward slash so that we are now able to unpack the entire path. Because what we actually want to do is we want to grab this file name here, because we're going to grab the matching alignments to that, because the alignment will be called BBA1 or L6N.align, and it's going to be in a slightly different folder. So this magic that is happening here in these three lines is exactly what is happening. So I'm then going and splitting on, we're actually grabbing the last value, which is index -1. You can see that we've now got the file name there, and then we're splitting again on a dot. So we've now got the file name and the file extension. We can then grab the file name, like so by grabbing the first index, and you can see that there. So that is grabbing the file name. We're then appending it using os.path.join. So we're grabbing the video path and the alignment path. Remember, if we go and take a look at our data, this is freezing up a bit. All right, so if we're inside of our data folder, we've got a folder called alignments in S1. S1 contains all of our videos, and alignments contains an S1 folder, which contains all of our alignments for speaker 1. And we've only got one speaker because I've cut down the data set. So if we actually go and run this load data function, this should return our pre-processed videos as well as our pre-processed alignments, which we should then be able to go and use inside of our deep learning function. Okay, cool. So take a look. So we've got a tensor return, which is 75 frames in length, which is 46 pixels high by 140 pixels wide by one channel, because we've gone and converted that to RGB. If we go and take a look, what do we have in our next cell? So this is returning a mappable function. Let me just quickly run you through this first up. So if we actually get what we're going to be getting back from this load data function is frames and then alignments. So if we go and take a look at frames, that is our frames data set. So you can see that we've got the shape there. If we wanted to go and plot out an example, so I could run plot.imshow. And if we just grab one frame, we should be able to show it. So you can actually see the person's mouth right there. Pretty cool, right? So this actually allows you to go and see all of the different frames that we're going to process. And as we go through each one of these frames, you're going to see the mouth move. So if I jump ahead to frame 40, you can see that the lips are moving. And this is the impact of subtracting the mean and the standard deviation. We're really isolating these regions that you can see highlighted in yellow here. Now, if we go and take a look at our alignments, this is the word representation of what is being said. So if we actually go and run this through, it should be num to char, which remember are our pre-processing functions that allow us to convert numbers to characters. We should be able to go and pre-process this. So if we grab the numpy value out of that, boom, you can see let's go and decode UTF-8. And we might need to go and loop through for x in. We're going to return x.decode UTF-8. And what are we getting there? It has no attribute decode. We just use that up there. Let's just print it out. Oh, I think we need to grab the numpy value. There we go. All right, and we should be able to go for decode UTF-8. No, it doesn't want to do it. All right, there we go. Much better. So this is the result of our transformation. So you can see it says bin blue at L6 now. So that is the result of actually going and transforming our alignment. So I've just gone and written print bytes. This is a long-winded way to go on ahead and do it. Not exactly the most efficient, but it is showing us our result. So you can see there that we've got our final end result. There's a way to condense this down as well. So I think if it's tf.strings dot reduce join, yeah. Unmatched. What have we done there? What is that in closing? Boom, there you go. So that is the result of our transformation. So you can see we've got bin blue at L6 now. So that is us going and undoing all of our transformation. The raw representation of that is just this, alignments. There you go. So each one of these individual characters. But remember, these just represent this specific sentence. So bin blue at L6 now. Okay, that is our set of alignments done. The last thing that we're going to do is we're going to wrap this inside of a mappable function, which is going to allow us to return back float 32s in 64s, and we're also going to be able to use our raw string processing. So this is just something that I noticed, and one of the nuances when actually going and dealing with TensorFlow data pipeline. So typically, if you want to go and use pure string processing, you got to wrap it inside of a tf.py function. So if we go and run that now, the next thing that we're going to be able to go on ahead and do is create our data pipeline. So let's quickly recap. So what we've now gone and done is we have successfully gone and downloaded our data using gdown. We've gone and created a pre-processing function to be able to go and load our video. We've defined our vocabulary. We've gone and defined a character to number function, a number to character function, a load alignments function, a load data function. We've then gone and tested it out using our test path, and you can see that we are now returning back a bunch of frames which show our person's mouth, which should effectively show the person's mouth moving when we stack all of these frames together. We've also gone and converted our alignments. So remember, this was our raw alignments. We've now converted it into an encoded sequence, which we'll then be able to pass through to our machine learning model. And we've also gone and created a mappable function, which we're going to need for our data pipeline in a second. Alrighty, let's jump back on over to our client. So that's our data loaded, right? Right-ish. We need to build a data pipeline. This will be used to train the deep learning model. Tensorflow will draw random samples from our data set in order to complete one training step. Oh, okay. Anything else? Yeah, we also needed to look at the data to make sure our transformations have worked successfully. Nice. Off to the pipeline we go then. So we're now on to creating our data pipeline. So let's go on ahead and do this. The first thing that we're going to go on ahead and do is import matplotlib, which I think we already had imported. So this might be me. Yeah, we did. All right, that's me importing stuff multiple times. Ignore that. We've already got it imported. But most importantly, we are going to be able to go and create our data pipeline. So this is probably one of the most important bits out of this entire thing, because creating the neural network is great, but actually having a data pipeline is just as important. So first things first, we are going to create our data set. And to do that, we are running tf.data.dataset.list files. So this is going to go inside of our data folder, inside of our S1 folder, and it's going to look for anything that ends in MPG, which is the file format that our videos are currently stored in. It's quite old, but it still definitely does work. We're then shuffling it using data.shuffle, and we're specifying the cache size to 500. So this will grab the first 500, shuffle those up, and then return a value out of that. We're then mapping it. So we're going to take the raw file format. So if I actually comment this out, let me show you what it looks like. So at its base file format, if I run data.asnumpyiterator.next, this is just going to return a file path, which is then going to be passed through to our load data function, which is going to do the splitting. And then we're going to run two sub functions, which is load video and load alignments. So that is exactly what we need to do by running the map function. So even if I run shuffle, you're still only getting back files, right? Or file paths. This isn't returning data yet, which is where the map function comes in. So data equals data.map, and we're running this mappable function. The mappable function is just wrapping our load data function inside of a tf.py function. And this is going to allow us to work with our specific file path formats, which now if I go and run this, and if I go and run this particular cell, we're actually going to get our data back. So this is returning our frames and our alignments. So if I go and take a look at frames, boom, that's our set of frames. We can run plot.imshow, grab one set of frames. Boom. We need to close this, not boom. Boom. All right. So you can see that we're now getting our data back inside of our data pipeline. If I go and take a look at our alignments, boom, you can see that we're now getting our alignments back. Okay. So then what we want to do is we want to pad this out, because right now we're going to have variable lengths for each one of these sets of alignments. So if I go and run this again, you can see that one's a different length. 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 And this is because there's going to be a different number of characters inside of each one of these sets of alignments that we've got over here. So what we can do is we can convert these to a padded batch. So we've then gone and overridden our data pipeline with data equals data.padded batch. We're batching into group sizes of 2. So each one of these is going to have 2 videos and 2 sets of alignments. We're then padding out our shapes. So we're not really going to pad out our videos. We are going to ensure that we have 75 frames. We're not going to pad out the actual image itself. We're just going to ensure that we have 75 frames for each one of these videos. And we're going to ensure that we have 40 tokens for each one of our alignments. If there's less than 40, it's going to be padded out to 0. And then we're prefetching to ensure that we optimize our data pipeline so that we're preloading as our machine learning model is still training. So if we go and run this full pipeline, that is brilliant. We can then go and run this particular line here, which is going to now load 2 videos and 2 sets of alignments. So you can see that we've now got 2 sets of alignments, and you can see that we've got trailing zeros at the end because it is padding out our alignment. Likewise, if we go and take a look at a frame, you can see that we should have 2 frames now. So if I type in len frames, boom, we've got 2 sets of videos inside of each batch. Okay, that is looking brilliant. Now, what we can actually go on ahead and do is run through this. So I'm going to run data.asNumpyIterator. So this allows you to iterate through exactly the same as what we're doing up there. You can see that by running .next, we're going to get so val0 is going to be returning our frames. then this is my favorite function, right? So image.io.mimsave actually converts a NumPy array to a GIF. So if I go and run this line here, so image.io.mimsave, it's actually going to take our data set, which is what we've gone and defined over here. And it's going to grab the second value, which should actually, it's going to grab the second instance of our videos. So if I could set this to 0 or 1 because we've got 2 sets of videos inside of each batch, and it's going to convert it into a GIF. So if I actually go and run this, inside of your folder now, you should have a file called animation.gif. And you can see that this is what our LipNet model is going to learn to decode. So purely based on the GIF that you're seeing, it's going to learn to try to decode what the person is saying and convert this to text. This is the amazing thing about this model, because we'll actually be able to take nothing but this types of data and convert it into a sentence, really. And this is going to get even better once we go and convert this onto our data set, which is probably going to come inside of another tutorial, but I wanted to get this base one out. Okay, so that is what image.io.mimsave does. We can then go and plot out our image, which you've sort of seen already. So plot.imshow, what we're doing here is we're grabbing our sample data set, which we've just gone and created over here. We're grabbing our videos. So index 0 is going to reference so let me explain this indexing or this subscripting. So the first 0 is representing that we want our videos. So that's what our first 0 is referencing. The second video is saying, give me the first video out of the batch. And then the third 0 is telling me, so the third 0 is giving me return the first frame. My head's blocking this. Frame in the video. Right, so if we wanted to go and grab the last frame, I could pass through 74, because remember we're going to have 74 or 75 frames per video. That is the last frame in our video. We could go and grab right in the middle, which is going to be 35, which you can see is the mouth moving. I could even go and grab the second video by changing this index to 1 here. So you can see that that is a completely different video now. And then we've also got our alignments, which we went and took a look at. So, oh wow, I didn't need to go and do all of that decoding. I knew I had a way more efficient way to write it. So tf.strings.reduceJoin, we're then going and looping through every single word inside of our alignment. And you can see that this is the end result. So bin white by N2 now, which is going to be the annotation for our first video over here. So if we actually go and take a look, this is doing this right now is grabbing our second video. So if we went and created the GIF for the first video, so that should have gone and done it. If we go and reopen our animation. So this animation that you can see here is the representation that we're going to be passing through to our neural network, which actually represents bin white by N2 now. So this is almost like moving chess pieces. It's not chess pieces, but that's sort of the feeling that you get, right? Or that's sort of the set of commands that we're actually getting out, or that a person is actually communicating back through. And this animation, so we're going to effectively produce a deep learning model which takes this input and is able to output this bin white by N2 now. Pretty cool, right? Anyway, that is our data pipeline now built. So kind of straightforward there. So we've gone and created a TensorFlow data set. We've gone and tested it out using the .asNumPy iterator method and using the .next method to grab the next instance out of our data pipeline. We've also used image.io.mimsave to convert a NumPy array into a GIF so that you can see what this actually looks like. And we have also gone and taken a look at the pre-processed images as well as the pre-processed annotations. Alrighty, that is our data pipeline and now ready for training. So remember, we've now got a data pipeline over here. We're not going to be splitting this out into training and validation, although you definitely could. But now we're just going to be running on this particular data set. Best practice is you split this out into a training and validation partition. But if you guys do this as part of the tutorial, let me know and I'll add it to the GitHub repository. Okay, that is our data pipeline now ready. Alrighty, on to modeling. I'm destined for the catwalk, man. Bruh. Seriously though, check out my pout face. I'm the male embodiment of Bella Hadid. Yeah, well, we've got to build this model now. We're going to use 3D convolutions to parse the videos and eventually condense it down to a classification dense layer which predicts characters. So single letters at a time? Yep, we'll use a special loss function called CTC, aka Connectionist Temporal Classification, to handle this output. Interesting. Why use that loss function? Well, it works great when you have word transcriptions that aren't specifically aligned to frames. Given the structure of this model, it's likely to repeat the same letter or word multiple times if we use a standard cross-entropy loss function. This would look like our model is way out. CTC is built for this and reduces the duplicates using a special token. But our data set was aligned. Yeah, you bang on. But when it comes to eventually subbing out the data with data that we create, it's going to be way more cost effective to simply use non-aligned data. Our model is going to be ready for it. Got it. Off to the catwalk then. The next thing that we need to do, as we told our client, is actually design our deep neural network. Although we're not going to be on the catwalk, we are going to be working with Tensorflow. So first things first, we are going to go ahead and import our dependencies. There's quite a fair few here. So we've actually got OS. Oh man, I need to go and clean up some of those imports. So first up, we're going to be importing the sequential model class. So from tensorflow.keras.models, import sequential. We're then going to be importing a bunch of layers. So from tensorflow.keras.layers, import conv3D. So this is a 3D convolution. So conv3D, TensorFlow. Absolutely brilliant when working with video. So we're going to be performing a 3D convolution or spatial convolution over volumes. It's used quite a fair bit for video processing or video classification in that particular example that I was sort of looking at previously. We are then going to be using an LSTM. So this is going to give us our recurrent neural network. Eventually, I want to convert this over to a transformer neural network so that we've sort of moving over to state of the art. We're using a dense layer, dropout layer, a bidirectional layer to be able to go and convert or pass through our temporal component when we're using our LSTM. We are also using, I think we need to clean this up, but we've got max pool 3D, activation, reshape, spatial dropout, batch normalization, time distributed, and flatten. I think I don't actually use all of those. They might be leftovers from me prototyping this, but we'll take a look. We've then got our optimizer. So from tensorflow.keras.optimizers, import Atom. And then we've also got our callback. So from tensorflow.keras.callbacks, import our model checkpoint. So this is going to allow us to save down our model every X number of epochs. I think we're doing it every single epoch. And our learning rate scheduler. So ideally, we want to sort of start out fast and then slow down as we get to our optimization point or the minimum value of loss that we could potentially get to. Okay, then we've got our neural network. So this is a couple sets of convolutions. We're then flattening it out using a time distributed layer. We've got two sets of LSTMs, and then we're using a dense layer to drop this out. Let me walk you through this. So first up, we're instantiating our model by running model.sequential or model equals sequential. We're then passing through a convolution with an ReLU activation with a max pooling layer. I could actually condense this down by just passing through activation over here. That's perfectly okay. This was again prototyping in its process. So then I've gone and written model.add conv3D. So we're going to have 128 3D convolution kernels. These are going to be 3 by 3 by 3 in size. Our input shape is going to be 75 by 46 by 140. And that is the representation that we've got from our data. So remember data.as numpy iterator .next. And if I grab the first value or the first value, we should be able to go, let's grab 0.shape. You can see it is 75 by 46 by 140 by 4. We're passing through that exact same shape into our neural network. We're specifying padding equals same so that we preserve the shape of our inputs. Then we're using a ReLU activation to give us some non-linearity to our neural network, and we are condensing this down using a 3D max pooling layer. So this is effectively going to take the max values inside of each one of our frames, and it's going to condense it down between a 2 by 2 square. So it's going to take the max value to be able to halve the shape of our inputs. Then we're doing pretty much the same 3 times. So except the only difference is that we're then going to have 256 3D conv layers or 3D conv units, and then 75 3D conv units, and then we've got this time distributed layer over here. So this is effectively going to allow us to have 75 inputs into our LSTM neural network so that we eventually will output 75 units, which represents our text-based characters. We've then got 2 LSTM layers of 128 units. We've got a specific form of kernel initialization. I actually found a great repo which shows the pure LipNet model, and they were using orthogonal kernel initialization. We are also going to be returning sequences so that our LSTM layer does not just return a single unit, it returns all 75. We're also specifying bidirectional, so we're passing our state from left to right and right to left because it is likely to impact how we actually go and translate this out, and I believe it's best practice and what was originally done in the paper. Actually, let me show it to you in the paper. So if we actually scroll up,
So they've got, there you go. So they're using a GRU as opposed to an LSTM. So they've got a spatial convolutional neural network. They've got a bi-directional GRU. We've got a bi-directional LSTM. And again, they're using CTC loss as well. Then we've got dropout after each one of our LSTM layers. So we've got a little bit of regularization and we're dropping out 50% of the units. So we've got a dropout after our LSTM layer and we've got a drop up after our other LSTM layer. And then we've got a dense layer, which is going to take in, I believe it's 46 units. So just taking our vocabulary size +1 to be able to handle our special token of vocabulary size. So you can see it's 40, so it'll be 41 outputs. So this means that we're going to have, our output should be, let's take a look. So it's going to be 75 by 45. This represents, we're going to get one output per frame that we pass through. And 45 is going, or 40, actually it's 41, not 45. And 41 is going to represent a one hot encoded representation of our final output. Now we are using a softmax activation, so we're going to be able to use an argmax value to be able to go and return the most likely value. We're also going to be doing a little bit of sampling, and I think we're using a greedy algorithm later on so that we get the most likely character returned back. Okay, that is our deep neural network. So let's go and create that. Have we not? We haven't gone and imported this, so let's import this. Let's go and create our neural network. So that is instantiating right now. Beautiful. And then what we can go on ahead and do is run the summary. So this shows you in a little bit better detail what we're actually building up. Let me zoom out. So we've got our convolutional layers, we've got our activation and another max pooling layer. Again, conv3D, activation, max pooling, conv3D, activation, max pooling. We've got our time distributed layer, right? So if you take a look at the last output that we're getting from our conv layers, it's going to have the shape of 75, effectively think of this as 75 time steps by 5 by 17 by 75. So that is the last set of output. Now what we want to do is sort of preserve that temporal component. So we keep it as 75 and then we're flattening this down. So we've got 6375 here. So this is just, let me add another cell. So this is just these sets of values flattened. So it's 5 by 17 by, what is it, 75? Boom, 6375, which is what you've got there, 6375. Then these values are then passed through to our LSTM layers, which have got 256 units. Actually, they've got 128 units, but it's doubled because we're bidirectional. So we've effectively got two sets of LSTM layers there. And then we're then passing that through to a dense layer. We've also got our dropout over here and our dropout over here. And then we're passing it through to our dense layer, which is going to output, as I said, 75 frames by 41 outputs, which are one hot encoded representations of our characters. Total parameters are 8.4 million. So it's large, but it's definitely no ChatGPT large in that particular respects. So that is our deep neural network now created. So again, you can step through this, you can tweak it if you want. If you come up with a better architecture, by all means, do let me know. I actually saw on papers with code, did they, grid corpus, that somebody might have already built it using attention. I haven't taken a look at this, but you can see they've got a CTC attention model, which would be really, really interesting to take a look at. But if you wanted to go and dig into that, by all means, do take a look. There's also this model here, which was on GitHub. This was the official model. So it is a brilliant example of how to go on ahead and build this up. It is a little bit more hardcore to step through, and the architecture is a little bit different to mine. But if you actually go into this particular GitHub repository, brilliant implementation of LipNet. Mine just works through, it doesn't use as much data and is a little bit more straightforward to walk through. Okay, that is the model summary. I'll include that link in the description below, by the way. All right, cool. So let's go and test this out. So this is going to suck at the moment, but I like to always do this when I'm prototyping a neural network, pass through some inputs just to see what we're outputting. So right now, if I go and grab our model and use the .predict method, we can pass through our validation or our original sample data, which we stored as val. And if we go and pass through val0, we should get some predictions back. It might take a little bit of time because we're first initializing it, so it'll be loading into GPU memory now. Let's give it a sec. Perfect. We now have a prediction. So if we actually go and take a look at the result of that prediction, you can see it's just returning random gibberish right now. So that is actually what our model is predicting. So 3 exclamation mark, KKK, bunch of exclamation marks, bunch of V's, bunch of exclamation marks, bunch of K's. So nothing crazy there. So we are just using exactly the same as what we did previously. So tf.strings, dot reduce join, we're then passing through, or we're using a greedy algorithm and just grabbing the maximum prediction return back. If I show you the raw prediction, what we're getting back, so if I just grab one example, so what we're getting back is a set of, let's take a look at the shape. So we're getting 75 outputs, each one of these represented as an array with 41 values, which is just a one hot encoded representation of our vocabulary. So if I went and ran tf.argmax and said axis equals 1, this is returning back what our model is actually predicted. So a bunch of characters. So right now we're returning the second prediction there. This is what it actually looks like, right? So a whole bunch of characters return back. If we went and ran this through our num to character pipeline, so 4x in that, and then if we go, num to char, pass through x, boom, boom, boom. You can see that we've got all of our characters there. And if we run tf.strings.reduce join, come on, buddy. Boom, boom, boom. Right, you can see that those are our predictions. This is exactly the same as this. Almost identical, right? Slight difference in that I'm using argmax over here rather than over here. But that is effectively showing us what our model is currently predicting. This sucks right now. We're going to make it way better. Okay, we can also take a look at our model input shape, and we can also take a look at our model output shape, which we've already sort of given or extracted when we went and ran model.summary. But that is our deep neural network now defined. So if I scroll on back up, what we've gone and defined is we've gone and imported all of our core dependencies for our deep neural network. We've then gone and defined our neural network over here, which is giving us a model which has a 8.5 million parameters. And we're able to go and pass through our frames to get a set of predictions back out, which right now doesn't look so great. But keep in mind, we haven't actually gone and trained this. So once we train it, we're going to get much better predictions. Alrighty, that is our deep neural network now defined. Let's jump back on over to our client.
We're on the home stretch. Just need to define our loss function and a callback so we can see how the model is progressing. Nice. Well, chop chop then, get coding. Let's do it.
So we're now pretty close to training our model. The first thing that we need to do is define a learning rate scheduler. So this is basically going to give us a learning rate of whatever we're passing through. If we are below 30 epochs, if not, we're going to drop it down using an exponential function. Alrighty, cool, that's now defined. The next thing that we're doing is we're defining our CTC loss. This particular block of code, I'm going to give original credit to this automatic speech recognition model, which I believe is defined somewhere a little further down. Was it from this one? I believe it was. Where's their CTC loss? CTC loss. Yeah, it's over here. So this basically allows us to use a similar method. So they're passing in audio waves. We're going to be passing through videos to be able to go on ahead and do this. So what we're doing is we're taking through our batch length, we're calculating our input length and our label length, and then we're passing it through to tf.keras.backend.ctc batch cost. So there isn't a ton of documentation on this, which is, funnily enough, a lot of the times you guys ask me, Nick, should I learn TensorFlow or PyTorch? Sometimes where I feel TensorFlow falls short is in some of the documentation within some of this nuanced stuff. So this is one example where I'd be like, I wish I'd gone and learned PyTorch, but it definitely works very, very well, regardless of that fact. Okay, so we've got CTC loss defined there. This is going to take in our Y true value, our Y pred value, our input length, which is consequently the length of our Y prediction value, which should be 75, and our label length, which should be 40. So this is going to take in our Y true predictions, which is going to be our alignments. This is going to be our one hot encoded predictions. This is going to be the value 75 because it's going to be the same shape of the output of our machine learning model. And then our label length over here is going to be 40. So that is our loss function defined. Then this is a lot of code, but really what we're doing is we're going to be outputting a set of predictions. So we're going to output the original prediction or the original annotation and then the prediction itself. In order to do that, we're using a special function called tf.keras.backend.ctc decode, which is specifically designed to decode the outputs of a CTC trained model, which we'll also use to make a prediction down here. So this is an example of a callback. So I've written class, produce example, and then to that we are passing through the Keras callbacks function, we are going to be subclassing that in order to be able to go and call this callback on every epoch end. So if we go and run that now, this should allow us to compile our model. So we're then grabbing our model, we're running .compile, which is a typical standard Python, or which is a typical standard Keras graph call in order to compile our models. So basically what we're saying is that we're going to be setting our optimizer to an atom optimizer with an initial learning rate of 0.0001. We're specifying our loss as being defined as our CTC loss function, which is what is defined over here. If we go and compile this, no errors, we're looking pretty good. Okay, the next three things that we're doing are we're just defining our callbacks. So we've got one checkpoint callback, which is going to save our model checkpoints. So this is we originally imported it right up here. So we imported model checkpoint and learning rate scheduler. We're now going to define instances of these. So model checkpoint is just defining where we're going to be saving our model. So we should probably just create a folder for our model. So I'm going to create a new folder, call it models. And when our model trains, we're going to save our example checkpoints to this particular folder. So it's going to be saved inside of models. It's going to be called checkpoint. We're also going to monitor our loss, and we're only going to save our weights, which means we'll have to redefine our machine learning model in order to load up these weights. We're then creating a scheduler. This is effectively going to allow us to drop our learning rate each epoch. So let's run our checkpoint callback and our schedule callback. And then we're also defining our example callback, which is going to make some predictions after each epoch just to see how well our model is actually training. So if we go and run that now, all that's left to do is actually go ahead and fit our model. So I'm going to bump up this number of epochs to 100 because the final model that I'm going to give you the weights for was as of epoch 96. So the last line is model.fit. To that, we pass through our data. If you wanted to have some validation data, you could actually just go and pass through validation data, specify validation data here. I'm not going to use validation data. That is not necessarily best practice, but you definitely could if you wanted to. So for the instances of actually keeping this relatively, this is probably going to be an hour tutorial regardless, but you definitely could go and pass through validation data there if you wanted to. So model.fit, we're passing through our data, we're specifying epochs as 100, and then we're going and passing through all of our callbacks. So we've specified callbacks, we're passing through our checkpoint callback, which is this. It's basically just saying that we're going to save our model every epoch. Our schedule callback, which is going to drop our learning rate after we get to epoch 30, and our example callback, which is going to output our predictions after each epoch so you can actually see how well or how terrible our machine learning model is actually making predictions. So we're actually not going to run it for the full 100. I'm actually going to run it for a couple. You'll see that it's actually training, and then we're going to be able to load up a couple of checkpoints. So let's kick this off. All things holding equal, we should be able to see our model training. Also, this is being trained on a RTX 2070 Super. So the speed that you're seeing there is effectively that. So you can see it's taking around about 4 minutes, 4.5 or 5 minutes per epoch. So let's give this a couple of epochs, and let's at least give this 2 epochs, and then you'll be able to see what the predictions look like.
A few minutes later.
Alrighty, that is 2 epochs now done. So you can see that this is epoch 1 and this is epoch 2. Now, I wasn't happy about the fact that I didn't have a training and a testing data set. So I went back to the data pipeline and I added those steps. Let me show you what I did there. So if we scroll on back up, what I did is I added 3 lines of code to be able to go and create this. So first up, I said that we don't want to reshuffle after each iteration. So I added that to the data.shuffle line. And then I added these 2 lines here. So first up, we're creating a training partition by taking the first 450 samples. And then our testing partition is going to be anything after that. So we're running data.skip to grab everything and assigning that to our testing partition. Then inside of the model.fit method, I've just gone and passed through our train data and I've set validation underscore data to test. I couldn't live with myself if I didn't actually go and split these out. So I went and did it to show you how to do it so that you effectively have best practice, because that's what we're all about here. Getting that little bit better each and every time. All right, cool. Let's actually take a look at what's happened. So this is epoch 1 here. So what you're seeing is, first up, this is the loss for our training data set. Down here, you've also got the loss. Actually, this is it's the same, roughly the same thing. This is the validation loss over here. So our training loss is 69.0659. Our validation loss is 64.34. So not too bad and not too far off. If we scroll on down to epoch 2, our training loss is 65.58 and our validation loss is 61.24. Our learning rate is still at 0.0001. And you can actually see some predictions here. Now, when I was first developing this, I was thinking, hold on, is this just performing like absolute crap? But what you'll actually see is that the closer you get to around about 50, 60, 70 epochs, the better this begins to perform. So in this line, you can see that this is the original set of transcription. So place blue in B7 soon. And then this is what it predicted. La, I, u. Kind of crap. Then we've got down here, la, I, ion. So again, kind of crap, even though that this was our original prediction. But give it a chance. So once you actually get to around about 50 epochs, the performance increases significantly. And you'll actually see that it actually starts performing very, very well. This brings me to my next bit. I've actually made the model checkpoints available to you so that you'll be able to go and leverage these yourself. That being said, you'll actually now have some checkpoints stored inside of the models folder thanks to the checkpoint, the callback that we've already gone and created. So we'll actually be able to go on ahead and use these. But for now, let's jump back on over to our client and then we'll be wrapping this up.
It's the final countdown. Some might say we're in the end game now. Yep, yes we are. Time to use this model to make some predictions. Let's roll.
Alrighty, we're in the final stages of this. So we are now going to make some predictions with a model that is not so crap. So first things first, we are going to be downloading the checkpoints. So the checkpoints that I've made available on Google Drive are after 96 epochs. So again, we're going to be using gdown to go on ahead and download this, and it is going to download a file called checkpoints.zip into our root repository. So if I go and run this, it should start downloading. It's around about 90 odd megs in size. As soon as you see it downloaded there, so you can see it's downloading, it's going to throw it into our models folder. Boom, that's looking promising. So it's now saved into our models folder. It's gone and overridden our existing checkpoints. Those kind of sucked anyway, so it's perfectly okay. Okay, and then what we're going to do is we're going to load the checkpoints into our model that we just went and downloaded. So using model.loadWeights, we're going to load up the checkpoints that are inside of this models folder. So if we go and run this now, that's loaded. We can then go and grab a section of our data. So let's actually go and grab test.asNumPy iterator. We're going to grab another sample. This is a little bit slow. It's something that I noticed inside of the Tensorflow data pipelines. And I think it's because we're using the skip method and the take method. So I think the skip method does take a little bit of time, but it's perfectly okay. Just give it a sec. It'll give you a sample back and then we'll be able to go on ahead and make a prediction. Let's give this a sec.
A few moments later.
Alrighty, we've now got some data back. I just spent a couple of minutes scrolling through Twitter while I waited for that, but we now have some data. Okay, this is looking pretty promising. So if we now go and grab a sample out of that, oh, we've already got a sample. I don't know why these two are redundant. We've already got this data. All right, so this is our sample. We can then pass our sample to our model.predict method. Boom, that has made our prediction. And if we go and decode this now, take a look. So these are our predictions. So you can see it's actually gone and written lay red with L7 again, lay green with G4, please. All right, drum roll, please. Let's actually see what the actual predictions or what the actual text was. Take a look. Lay red with L7 again, lay green with G4, please. Actually performed pretty well. So take a look. So this is actually the result of passing through these images. So it's actually decoding relatively well. Now, if we wanted to go and do this using another video, then we'd actually be able to go and load this up using the Streamlit app. And that is what I am going to be doing inside of the Code That episode. If you guys want it, comment below, make sure you give it a like so this video gets a little bit of airtime. But let's go and make another prediction. So if we went and grabbed another sample, so if we went and ran this again, so those are our predictions. And this is what, well, we should really swap this around. So this is the real text. These are the predictions. So the original text was set green by J1 soon. So you can see that we're actually grabbing data out of our sample. And over here, we're grabbing the decoded set. So this should actually be there to make a bit more sense. All right, so let's actually go and run another sample. So if I go and run this. So the original text was lay red at E3 soon. And then the second sample was place green by R3 again. Now, if we go and run our decoder, let's minimize that. Well, let's see what our model predicts. Oh, we actually need to go run it through decoder. Boom, take a look. Lay read at T3 soon. So it said T3 soon. Our model, our actual text was E3 soon. So not too bad. What about over here? So place green by R3 soon, place green by R3 again. It's actually performing relatively well. My personal thinking though is that this doesn't fully tie it together. I still think we personally need the app. So again, if you reckon that we should go and do the app or build another tutorial for the app, let me know in the comments below and we'll be able to build this up. But this is actually making valid predictions. So if we wanted to, we could actually go and load up a new video and try to test this out. So if we say load data, and let's go and grab a video, for example. So if we go into, this is completely unplanned. So let's actually see if this works. So if I go into S1, let's grab the path to this particular file. So if I go and pass this through, and we're going to say data.backward/s1 that. All right, let's see how that goes. We need to wrap this in tf.convert to tensor. Okay, so that is our data set. So this should be BBAF3S. So let's go and find that video. All right, so if we go into videos, actually we're not going into videos, we're going into YouTube, and then let's put my headphones on so I can hear this. Going to lipformer, data, what do we get? BBAF3S. S1, BBAF3S. So this is the video.
Bimblu F3 soon.
Make this louder.
Bimblu F3 soon.
In blue at F3 soon. So this is our data. So we're actually going to have our sample, and we are going to have our, our text. So let's go and say, let's add another section, test on a video. And this is going to be outside of our existing data pipeline. So we'll test this out. So we've now got a sample, and we can pass through, if we call it sample, we should be able to just do this. So if I copy this, and then what we're going to do is we're going to pass through the sample to here. Actually, if we just call this sample, we should be able to use it without much change. Call that 0, boom, okay. What's happened there? That's probably because we've only got, we need to wrap this. So if we run tf.expand dims, and then pass through axis equals 0, boom, that should make a prediction, cool. And then I'm going to copy this, paste that there, and I'm going to copy this, paste that there, and I'm going to copy this, paste that below again. Okay, let's minimize this. So what do we got? So we've got our sample. This is us custom loading a specific video, which we just played, which sounds like this.
Bimblu F3 soon.
Cool. All right. So we should expect this to print out Bimblu at F3 soon. So if we now go and run this should make a set of predictions. If we take a look at y-hat, that's our set of predictions, .shape. Cool. All right. So we've got 75 by 41. So sample 1 is going to get out our real text. So 4 sentence in sample. What have we done there? Cannot iterate over a scalar tensor. So if we just go and wrap, sample 1 should be fine. 4 sentence in sample 1. It doesn't like this because it is not wrapped. So if we do this, I just wrap it inside of another set of arrays. Okay, cool. So that is our real text. So Bimblu at F3 soon. Let's go and validate that.
Bimblu F3 soon.
Beautiful. Okay. And then if we go and make our predictions, we need to go and run it through this first. And I think we need to wrap this tf.expand dims, comma 1, comma 0. Nope, no bueno. What's happening? Transpose expects a vector of size 4. This is only going to be 75 over here. What have we done? But input is a vector of size 3. What's y-hat returning? .shape. 1.7, that should be okay. Okay, that worked. bin blue at J3 soon. So it wasn't too far off. That's not too bad. So this is actually on a live video. So if we go and run this through this pipeline now. So this is what was actually said. So bin blue at F3 soon. It predicted bin blue at J3 soon. So not so far off. Let's go and try another one. So let's get freezing up. Come on. What about this one? PRAC. Let's copy this path. All right, so we're going to do dot //. So you can actually do it on a separate video without having to use the data pipeline. If we go and run this now, take a look. So the video said place red at C6 now. Our model predicted place red at C6 now. Let's go check this one out. So PRAC6N. Oh my gosh, guys, how cool is this? PRAC. PPPRAC. Wow, finding it, it's half the battle. PRAC6N, this one.
Place red at C6 now.
Hold on, did that? Show me it. Show me it. Place red at C6 now. Guys, that is bang on.
Place red at C6 now.
Place red at C. As if that isn't absolutely awesome. So it's able to load up a video and decode it and use lip reading to actually go and transcribe this. Let's try another one. What about this one?
Set blue in A2, please.
Set blue at A2, please. So let's go and copy this name. Paste that in there. All right, so let's just quickly play it again. Keep in mind, our model doesn't get any audio, right? It's just using that little GIF that I showed you to be able to decode this. So if I play it.
Set blue in A2, please.
Set blue at A2, please. That's what we're expecting. All right, set blue at A2, please. So this is our annotation. Set blue at A2, please. Set blue in A2, please. How absolutely amazing is that? Let's go find another one. What about, let's get one from up here. What about L? So LBID 4P. So again, you could try out a whole bunch of these videos. So LBI, let's go and play that video.
Lay blue in D4, please. Lay blue in D4, please.
Lay blue in D4, please. So again, let's go and take a look. So this is the actual text. So lay blue in D4, please. Let's run it through our model. Oh, we've already made our predictions here. This should really be down there. Let's run it through our model. Lay blue in D4, please, guys. How absolutely amazing is that? It's actually making valid predictions. Oh my gosh. I get ecstatic every time I see this. All right, let's do another one. BRAS 9A.
Bin red at S9 again.
All right, let's play that again.
Bin red at S9 again.
So it's BRAS 9A. I really want to build this app now. All right, so bin red at S9 again.
Bin red at S9 again.
Right, okay. Keep in mind, it's not using any audio. All right, run it through our model. Bin red at S9 again. How absolutely amazing is that? So that is the LipNet model now built. Hopefully you've enjoyed this tutorial. We've been through an absolute ton of stuff. Just to recap, we started out by installing and importing our dependencies, building our data loading function, which we eventually did a little bit of tweaking to so that we would have a training and testing partition over here. We did create our data pipeline. We then went and built and designed our neural network, which kind of mimics what was originally in the paper, a little bit of a set of tweaks. And then what we went and did is we went and trained it using a custom loss function, a custom callback, as well as a learning rate scheduler. And then last but not least, we went and made some predictions, and I just went and tested it out on a video. So you've got the script to test this out on really whatever video that you want. But ideally, it's going to perform well on similar images or similar videos to what we've actually gone and trained on. But we could definitely go and fine tune. Let me know if you'd like that video. For now, thanks so much for tuning in. I'll catch you in the next one. Peace.
Thanks so much for tuning in, guys. Hopefully you've enjoyed this video. If you have, be sure to give it a big thumbs up, hit subscribe, and tick that bell. It means the absolute world to me. But it doesn't stop here. We're going to be taking this to a next step if you want it. Should we learn how to be able to replace it with videos of ourselves to be able to go and lip read videos in general? Maybe we should convert this into a Code That episode and build up a standalone app to be able to use this out there in the real world. Let me know in the comments below. Thanks so much for tuning in, guys. Peace.